Okay, good afternoon. I think we can start our session. My name is Jiří Navrátil. I come from the Czech Republic, working for CESNET, and I should be chair of this session, which is called Software-Defined Networking. We will talk about the open flows and all these things around. We have three talks. The first one is from Niels Ward, working for Juniper. The second, Eduardo Jacob, which is from the University of Basque Countries, and Eric Pujol from LBL, USA. So there's a first is the Niels Ward. He's working as a as I've said for the Juniper, and he defines the new strategies for UNOS, and he deals with the topics like the open flows, BGP, Auto, and other important topics. So, Niels, floor is yours.
A little bit of history before handing it over to the speakers. Thomas Schmid sitting over there, and I.
Oh. As I'll just shout. Oh, that's not needed. Cool. All right. So as mentioned, I'm Niels Swart. What we do at Juniper is trying to figure out which new technologies are interesting enough for our customers and research partners to go and try out, regardless of what the potential effect is on the rest of the business. So we try to find new technologies, try to figure out what is going on with them, prototype them, bring them out to customers, figure out if there's value. If there isn't any, we'll just we'll leave them. If there is value, we'll continue with it. So this talk will, the 30-second pitch is, there's a lot to be said about programming the network from anything that hovers above the infrastructure. And one could call this adaptive networking as part of software-defined networking. But adaptive networking isn't at all new. So we'll talk about the history, about some of the challenges that are coming up, specifically around how we define the primitives between networks and applications, what steps we can take, and then ultimately where we think this ought to sort of land. So adaptive networking is not at all new. I think the amount of topics that were discussed sort of 5 years ago at Terreno conferences, and then sort of this year about bandwidth on demand. If we take a look at internet service providers, where bandwidth on demand has been one of the functions for subscriber management for a long while, it has always been there a little bit. We had network-aware applications, we had application-aware networking. Some parts of this are called self-service portals, where you go in and do everything that a network operator used to do for you. That's all fine. It went back to 2001. Has anything changed? We went from self-service portals to integrations with application ecosystems, to IMS, tie-span type of infrastructures. Has anything meaningfully changed? And from our perspective, yes, things are starting to change. And the first thing that has to change, that the integration that is needed for these applications to talk to the network has to become much, much simpler. Now, the real question is, what are some of the enablers? Is OpenFlow an enabler for that particular problem, or will an OpenFlow SDN-enabled infrastructure be better capable of accepting information from applications and vice versa? So these are all sort of very valid questions. Is this truly sort of on the way to solve the bigger problem here? Well, from our perspective, and we've done quite a bit of research on this with our customers, both service provider and enterprise customers, what we've actually found is that there's a profound divide that is holding everything back at this point. Everything meaning further innovation in how end users view the communication service that they take from networks. And that divide is what we have coined the application network divide. It's a divide between the software developers that are active in generic applications, the Microsoft Office of the world, SAP, Oracle, those application developers don't necessarily care about what the network has to offer, what it can offer. There's actually a bit of a brick wall between these two worlds, and it's kind of hurting us more than it's helping us. You know, in the past there was a good reason for these to be separated completely, but nowadays it's gone a little bit too far from our perspective. We have separate budget lines, we've got separate reporting structures for this. It's kind of a problem. And what you could coin this as, there's an application world and there's the network world, and the divide that is between them has existed, for the most part, almost forever. And it impacts everyone. It impacts everyone who works on the network side because they're always at the short end of the straw when it comes to budgeting, and it impacts the folks on the application side because they don't necessarily find it easy to interact with those people who generate the communications infrastructure for them. As a result of that, there are applications that are trying to get closer to the network, and networks getting closer to applications. And what you get here is that applications starting to guess and probe. This is one of the examples here is variable bitrate video encoding, where what you're trying to do is push as much data as possible through that infrastructure, whether or not you're allowed to or not, whether or not you're going to break something or not. By default, in that case, the application will just probe and will guess, what the capabilities are. On the flip side of that is the network. The network will continuously derive and spy. It'll do DPI, various functionalities of flow tapping, NetFlow, CFlowD, all that stuff. And it's very interesting to see that these groups of functions have collectively grown in silos, but never has there been a bridge that spans between those two. And actually, to that point, is that true? Is it indeed the case that there's a gap between these two worlds? And from what we can see, that's absolutely the case. What true levers are there today that you can use as an application developer to influence what the network itself does? And when I mean levers, this is an actual interface, somewhat like a uni into the network that affects the behavior or retrieves information from the network such that the application can be made better. In reality, there are either too few, and those that are there are highly technical and highly specific to networking in general, or networks in specific. So there's a lot of integration work that is needed in order for your application to play nice with a network and actually have a proper dance going on. Is the problem perhaps to be found in the way we talk to each other? And I'll talk about that a little bit more. We truly feel that the way we're currently discussing network services is very much network-centric. It is those things that are interesting to the network, bandwidth, latency, jitter, quality of service, that is most interesting to networks, and that's the language that we like to be talked to. But in reality, most application developers either don't know what the effect of one of these is on them, or just simply couldn't care less. For them, it's about an experience. It's either good or it's bad. So from our perspective, there's definitely a bit of a language issue. So do we need a network Babel fish, perhaps? Something that chirps into our brain, this is what the applications really want. Maybe. What I think we would be better off with is if we can find newer levels of abstraction that help us explain, both from the network world out, what it is that the network can offer, and enable application to tell us on their terms what it is that they need and require from the network. And the reason for this really is to make sure that the network that underpins most of the service that everyone uses on a daily basis these days is able to deliver what is needed at a cost-effective manner. So to what end do we want to enable this abstraction and enable this communication? For better billing flexibility, for instance. Creation of new services that we currently haven't thought of yet. A wholesale move to on-demand services. Bandwidth on demand is a key topic here, but moving even beyond that, basic connectivity bandwidth on demand, it could be user groups on demand. And then optimization across multiple layers is best done if you have as much information as possible across those layers. And in abstract form, that could be made useful for the network without being burdened too much by the application, and vice versa. So why are we saying that the on-demand characteristics ought to change? Why is more abstraction needed, or different types of abstraction? Well, we actually think and believe that it's the application itself that can adjust fastest to what's both available and can tell us faster than and can tell us much faster what it is that it wants from the network. Now, the important point for us to make here is that it's not necessarily the case that this is an IT operator or a web interface that will do anything anymore, but it is literally the end application that runs on a VM somewhere, runs in some kind of environment on your smartphone that through abstraction tells us, this is what I want from the network. So the way we look at this is there are two major things that have to happen. One is applications have to be enabled to inform the network of the desired behavior. This goes back to the point of new abstractions are needed because we don't think that applications can tell us what bandwidth they need. It will be post-fact that we know what bandwidth they used, but they likely cannot tell us what they need up front. Nor is that any given measure of what we could deliver for them. Likewise, on the way back, it's the network that should be able to inform the application of all sorts of interesting information that lives around it. This could be information along the lines, and we'll see some examples here of how somebody is connected. Somebody gave an example yesterday, actually, that talked about, wouldn't it be interesting for your end user, the server instance that runs somewhere, to know how the end user is connected through, optimal Wi-Fi, 4G, or some edge or GPRS service. That on its own, in other words, low, medium, high type of bandwidth available, could tell the application server to send only half of the information that's there. So in reality, we want to make sure that this bidirectional communication is enabled. And the bidirectional communication has an interesting side effect, and that is that the edge of the network is the one where the highest rate of change is needed. If you allow applications to influence what your network does, then in turn it means we have to process a lot of that at the edge, or at least the edge will be the one receiving that those type of changes. And the most crucial part yet, and those of you who've had the fortune of listening into some marketing folks somewhere else, it can capture intent. If you have an application that can tell you up front, this is what I want, that is intent. And intent allows you to model for the future as well as model for the present. It's the current lack of intent or knowledge of intent that basically presents us on a daily basis with a challenge of scaling up our networks even further because we just have to process all those packets that are coming at us. And if we know intent, or even if we start to register a trend, then we can sort of plan for it ahead. Now, what could you do and how should you look at this? Is this a one uni that fits them all? Well, the answer is not really. We've got sort of four major players here. And I promise I'll get to the point of SDN in a second. But we've got four major players here. We've got end users, we've got applications that live anywhere, we've got content or information that lives anywhere, and then we've got the network that, I'm a network guy, so I put that smack in the middle. But these four major players are the ones that have to interact with each other. And depending on which arrow you're looking at, there might already be activities in standards bodies or research activities going on, but in general, this information flow with the various types of abstractions will need to take place across all of them. And what we'll see as well is that in some cases within that network, we need extensibility for it, and that's where OpenFlow and SDN come absolutely into play. So let's give some examples. If we were to be able to influence between, or have bidirectional feedback loops between applications in the network, what could you do? I told you a little bit before that this could allow us to express the capabilities and limitations that are currently present. Anyone who's been to conferences where Wi-Fi sucks basically knows that that's a limitation in the way the infrastructure is built. But if all of the applications that are run over the network would know that your conference Wi-Fi isn't all that well or all that good, you could make sure that you're sending less bandwidth there. Likewise, for end users that live sort of everywhere, very much sort of moving, what you could look to in the future is to say, I have high, medium, or low amount of bandwidth available, or I'm running these services in addition to what's already there. Registering of intent. I think intent is very much the keyword for things like application network interaction, and will become a critical component of SDN and ultimately OpenFlow. You're able to augment end user sessions with useful information around you. What if Facebook were to know that we are all in this room? not because you've checked in on Facebook, but because the network is able to tell Facebook that you're all in the same location because you're connected to the same 3G cell site that's here. And likewise, some more examples. Flexible adjustment and creation of communication. The notion today of creating slices through your network is very much something that we look at from a research perspective, from a specific group of people that want to communicate with each other for a very long amount of time, or at least measured in hours and days. What if you were able to create closed user groups or closed application groups within various networks as if bubbles can start to appear? That could be interesting. But the only way that's going to become interesting is if the way this is exposed to applications is both simple and effective. And then sort of assurance of service is a topic that we'll talk about in a little bit more. I think it's safe to say if you look at this, there's a lot of research that is ongoing, but also has to kick off in order to make this happen. Because it's fine for us to come up here and say this should be done, but the question is, can it be done? And what we've actually looked at in more detail over the last year and a half, 2 years of us working on SDN and OpenFlow is that there's another inhibitor. This rate of change component that we talked about earlier is fairly well understood in mobile networks. It's very well understood in wireline networks, but it's not widely understood for entire infrastructures. So as rate of change goes up as a result of this interactivity, then how do we validate the network as a whole? How do we formally validate network operation in a way that we can actually say that this worked today, it worked yesterday, and it's going to work in the future? And how do we do that quickly? In other words, if I make a change or if I suggest a change, how do I validate this before actually going and doing it? So I've got two hypotheses that basically aim to guide future research if possible. The first one is that advances in this test and validation space will help make higher rates of change acceptable. In other words, many of the networks that are operated out there today are concerned with the rate of change. I don't want applications to talk to my networks. I don't even want things like OpenFlow because the rates of change are so incredibly high. So my first hypothesis is that the advances in test and validation, in order for us to be able to say, I can guarantee you that in the past, in the present, and in the future, this service will work because I can quickly validate it. If we have advances there, then that'll help us make higher rates of change acceptable. And the second one is, I think most of the network operations teams out there today are mired in details of mundane operational tasks. I say mundane in air quotes. I mean, this is bread and butter work of connecting users, troubleshooting infrastructures. And those mundane operational tasks have to take considerably less effort before higher rates of change can be even imagined. In other words, if it already takes you 3 hours to provision a new part of the campus, or even a number of days, then how can you even imagine making higher rates of change possible or allowing students to slice through part of the infrastructure? So what we want to create is not just virtual networks, but troubleshoot connectivity end-to-end and make sure that that's done in such a simple fashion that you can start to move your attention not away from those base functionalities, but towards what new services can be created. So on our trajectory from where we are today to where we could go when applications can talk to network, then I think it's safe to say that everything is about stacks these days. There's the network piece of the stack that will have to open up new and interesting APIs towards in the direction of applications, and applications will have to learn and will likely accept web service APIs to be used. Now, the layer in the middle that's missing here in this picture is sort of orchestration across the networks. Orchestration is this wonderfully complex and both fantastic new name for OSS and BSS systems. But in principle, what it means is that across not just one network, but multiple networks, you should be able to arbitrate resources and figure out where should stuff go. And what we've seen is that a lot of the inhibitors for making change in the network lie exactly in this orchestration across the network. In other words, mundane things like understanding topology take a very long time. So what we've done in a simple step moving forward is create logical blocks that said, what areas of research and protocol development could we go and tackle and make sure that we understand real-time topology much better than we did before. That's where IETF work around ALTO, application layer traffic optimization, and BGP-TE, which is taking link state and traffic engineering database state and pushing it into a BGP session so that others can use this information. Now, as soon as we have real-time topology, then the next step can start to happen. Namely, I can start steering traffic from one place in the infrastructure, from call it a controller or an orchestrator, and push paths through the infrastructure. And after I'm done doing that, I now have the capability of selecting traffic at a high rate, either selecting it to accept it into this newly created service path, or push it into a controller facility that can take a further look at this traffic and decide what else to do with it. And this is where OpenFlow comes in from our perspective. And this is by no means the only three blocks of information API exchange. There might be others coming in at either higher level or lower level. Now, how do we make use of this? Where does this fit in? And from our perspective, this starts to fit into something that we're working on in our team, is to see if we can cobble together an orchestration framework in a way that's not necessarily commercial product yet, but makes use of existing tools that are out there. So what we would have is, in red, somewhat of an orchestration component that has a consistent state database or a controller database. Above that is those application APIs that we talked about earlier, web service APIs, and below that we've got the network interfaces down into the infrastructure. And this is a combination of both OpenFlow, and for those networks that are not greenfield, it will also contain other interfaces that are there. And what we think is very interesting is to expand that and make use of the capability of plugging in new functionality inside of this controller. So the key two takeaways here are that we want to present usable abstract interface to the orchestration layer, and this is something we can certainly do as a networking vendor together with the industry. But then some other work has to happen to present usable abstract interface to applications above. Think of Amazon Web Services, the API that kind of grew into the role that it currently is as a de facto standard. Something like that we need for network services as well. In order to aid in sort of talking about this, we've created a bit of a framework model that basically is a bit of a hamburger diagram. We love to talk about boxes underneath, and usually there's a variety of devices. Element APIs, we've got tons of those, CLI, XML. And by and large, we have multiple management systems living in any operational infrastructure today. But the most important thing that most of our customers are working on is on this notion of workflow. In other words, how does the network fit into the workflow of connecting business customers or residential customers into the infrastructure? And ultimately, after we're done focusing on that area, we can look at how do applications actually influence what this network does. So in this particular framework, and I'm slowly running out of time, unfortunately, in the network programmability framework that we have, where should we place the various things that are happening? OpenFlow, SDN, and more of that. So the SDN focus really is on making sure that that management layer, together with the element APIs and the underlying forwarding elements, are taken care of. What we have seen, though, is that most customers are still viewing that as a subset of the network infrastructure. OpenFlow on its own sort of fits in as one of those element APIs, and certainly within SDN, there's a bit of an industry debate on that, but it is the most interesting interface that we currently have there. And then from our perspective, we like to focus on the entire problem space. Not necessarily to solve all of it, but at least to make sure that whatever solution we bring in part of the infrastructure fits in the entire picture of workflow and applications. And the way we split that up is to make sure that, one, we focus on reducing the burden of these, quote-unquote, mundane tasks first, and then figure a way out to bridge this application network divide through programmatic control. So the slides are posted, and in the interest of time, I won't spend too much time here, but abstraction is actually a really hard problem to solve. Because if we let ourselves work on the abstraction, then we're going to be somewhere in layers 1 and 2 and focusing very much upwards. If we let the software guys only work on abstractions, then we're going to get very much a top-down view. And where the two will meet is probably where the most interesting abstractions will start to appear. So what's relevant to both? And then, interestingly enough, we have a lot of protocols already today. Where do they kind of fit? And what we've started to do is map those out between the amount of abstraction that's possible and the amount of rate of change that it enables. And what we found is that certainly rate of change for some of these newer protocols is very high, but the level of abstraction or complexity that it can take care of is not necessarily that high. So it's very primitive, fast but primitive. What we're actually looking for, long term is there one thing or are there multiple things that will be able to go up on the abstraction portion as well as the rate of change? The clear note, though, is we need usable abstraction. And the way we get to usable abstraction is probably by trying hard together with our customers and research partners. And what we're doing internally within Juniper is making sure that we approach this in a lean startup fashion, where we want to rapidly iterate with our customers to make sure that we have skin in the game as well as our customers, that we fully understand what the problem is that's happening. So it's the traditional build, measure, learn type of approach. And it's, to be honest, for large companies, it's actually very scary to go there, because it requires you to accept some point in time that you weren't right. You have to go back and do something different. So the way we think about this, is sort of two axes. We've got a high rate of customization that's possible, certainly in the early stage, and then that ultimately feeds into standardization. And what you'll find across various industry initiatives is that there's deep customization possible today. This is where you find SDKs. Then there are early implementations of standards or workgroup drafts, and then ultimately, high number of standards will emerge sort of in the near future. And some of this we found will be helped by sample code that will be made available. So one of the ways that we approach this here, specifically around OpenFlow, but also BGBT and Alto, is to make sure there's sample code available to speed up this overly customized single vendor type of approach into a standardization track, so that more people can start to use this technology. There's a bunch of work in progress on our side. Feel free to to chase us down here in this particular event. But safe to say, yes, we're interested in OpenFlow. We've got solid plans for that. Yes, we're interested in BGBTE. The entire SDN framework is what we're currently looking at, and working actively with a bunch of folks in the industry. Actually, it brings me to the almost last slide. So what are we doing with the industry? So first and foremost, OpenFlow, Open Network Foundation is where OpenFlow is being standardized. We're an active member. We're contributing to some of the newer specs that are coming out, specifically hybrid operation, where the reality of everyday networks has to be taken into consideration of bringing OpenFlow flexibility into the picture. And the other part, this is a collaboration between research, universities, and commerce, is Open Network Research Center, where we're an active sponsor. And essentially, this is where some of the diagnostics and tooling that we talked about earlier is going to be actively worked on and ultimately propelled into the industry. Then there are a bunch of other industry standards bodies. Obviously, IETF is worrying nowadays about SDN and what that effect has on additional work that's happening. ITU has started with the Future Networks initiative inside of ITU, and then obviously a number of research areas here. So to conclude, and then I'll hand it back over. So what's next? From our perspective, let's get to the point that we can have applications talk to networks and networks talk back to applications. That's where a lot of the value is for end customers. That's where a lot of the research problems have to be, are already being addressed in the research space, but should be addressed a little bit more. So in order to solve some of these hypotheses, more research should go into things like formal validation. Likewise, on the quote-unquote mundane tasks, we should actively focus on freeing people's time up to actually work on some of these new things. And with that, I don't know if I have time for questions right now, but thank you for your time.
Thank you, Niels. So one short question, okay? Go ahead.
Bram Peters from SurfNet. We had a very inspiring presentation this morning on IPv6 and network neutrality. How do you combine that with having applications control the network, which is probably not very neutral?
That's a really good question. I may need to come back to you on that one. My initial thought on net neutrality versus applications controlling it. Today, you're already influencing what the network does with your application. And it's fairly uncontrolled. There's not really policy around it. I think what this will allow you to do is get to abstractions, and this is an industry thing, this is not necessarily one vendor, where you can create a level playing field. If I want information and I make that same information available to to all the other players in the market, then it's the choice of everyone else to see if they are going to implement it or not. So I think your sub-question there is, do you want to have sort of more control over the network infrastructure or not? And that's you know, it's hard to say. We see customers have a lot of interest in it, and I think legislation you know, should focus at the goal there, and that is create a level playing field. And you know, doing that with additional hooks should definitely be possible. Right. Thank you.
Thank you. So, in next talk, we will go from the strategic approach, which had Niels, into the practical approach. And Eduardo Jacobs, he is the associate professor in the Basque University countries, will have a talk deploying OpenFlow in the production at the University of Basque Country. Okay, Eduardo.
Thank you. Thank you, Niels, for the presentation. Well, first, this is the agenda I will try to follow. There is a presentation of the research objectives we had for this setup. I present a very short explanation about OpenFlow because if you are not aware of what OpenFlow is, it's perhaps somewhat difficult to follow the presentation. We'll present the evolution of the network research in our university and how we finished deploying EA2 OEF. We explain about the identity-based configuration and just a quick update on an experiment we are running that shows how this tool can be used for develop research. We will finish with some conclusions. The University of the Basque Country is the public university of the Basque Country in the north of Spain. It's a generalist university. It has a great amount of students, but it covers all field of knowledge. So it's not a technical university, it's not a polytechnical one. So the IT services have to give service to all those peoples. We have been involved in OpenFlow some time, and this is one of our first results on the OpenFlowness in. Well, I won't explain this too much. If you try to do network research in your university, you will inevitably be faced with IT services. Normally, you will ask for things that they are reluctant to give you. On one hand, because it sometimes takes too much time to set up things, and it's sometimes for a short time. They don't like to have many researchers as clients. They prefer to work. But anyway, I think this is a very well-known point, so I will not develop on that. Well, just some ideas about OpenFlow. OpenFlow was created in Stanford to support the clean slate research on future internet. Originally, it was targeting a research network, and now the interest is growing to other areas, data center, mobile, virtualization, many kind of technologies. It's based on the flow concept, I will explain later, and we have just had some information about the Open Networking Foundation. It's the organization that maintains and develops the SDN concept and the OpenFlow protocol specification. There are by now more than 60 companies from every part of the IT ecosystems. I mean, there are services providers, there are telcos, there are chipset manufacturers, everybody's there. They like to say that they have a high speed and minimal standardization. I mean, they tell that they are only devoting to OpenFlow and very specifically to the smallest part possible. Well, perhaps the concern is not very clear how universities and research institutions can propose, participate, or perform oriented research, because the access to the process is not open, is not free. So if you are not lucky to be in those universities that are in their own lab, you don't have much chances. Just a quick idea on how is flow on the flow table. This is a very old slide from the first presentation of Enigma Neon. Here we see that for OpenFlow, flow is no more or less than a match over several headers. I mean, there are several headers. This is the headers that were in version 1.0. And every time you apply a mask that selects part of your traffic, you have defined the flow. For every flow, you can select some actions. Can be forward the packet to a port, can be encapsulate and forward that frame to the controller, drop the packet, send to the normal processing, or modify fields. You have also some statistics there. For example, if you want to configure a switch, it's very easy. You only have to set up a rule that say every time you find a frame that has the MAC destination address, this one, just forward it to the port number 6. That would be a real switch. You can do flow switching. Flow switching could be as concrete and specific as unique as this one. You can apply all this mask and do it something with it. You can implement a firewall. You just say that everything that has a TCP destination port of 22 is going to be dropped. So the whole stuff consists on updating this flow table on every switch. That means that the standard switch you had, in which most of the intelligence was located in the switch itself, now is in a central controller. This controller can, in fact, control several switches, a whole infrastructure, and it's important to note that the OpenFlow protocol defines only how the controller insets rules in that flow table and gives information to that switch and retrieve information. OpenFlow is only about that. There are other protocols for the Open Networking Foundation for configuration, but this is what OpenFlow really is aware. Just if somebody is having some concerns, what happens if the controller breaks? Well, it can break, the link can break. It's always possible to define default rules that allows you to keep your network running. Well, another part of the Stanford ecosystem is the Flow Visor. Flow Visor is an intermediate controller that allows you to partition an OpenFlow switch infrastructure in several addressable ways, with the result that you can have several controllers running over the same infrastructure. That's what Flow Visor is. You have to define a slice policing, a slicing policing. You must define which are the rules that define one slice and differentiate it from other ones. But that's all what is needed. One important thing when we have to speak about OpenFlow is that there are many protocols versions right now. It's not there are many, but there were some early implementations. After that, version 1.0 appeared. It's the most widely deployed. And after that, 1.1 appeared, but ONF entered the scene. And between these two following versions, I think there are less than 3 months. So I mean, when they were speaking about quick standardization, they are really, truly. It's not easy. That's why nowadays, to the best of my knowledge, there are no implementations, neither of 1.2 or 1.3. There is, I think, one implementation of 1.1. And what we are using for our setup is version 1.0 with a max subnetting with a fixed field. That is required to our implementation. Well, we had several objectives. From the objectives towards our university, because this is a strategic research project from our research group, we wanted to tell them that it was possible to support network research in an organized way. We wanted to show them that it would be possible to support network experiments without disrupting the traffic, without giving problems to them. The software-defined networking was an appealing technology, so I think that interested them. There is also a sociological issue that is advancing in a mixed IT research management of the network. Nowadays, IT management is a pure technical management solution, like the heat and solution of the buildings. And our idea is try to investigate in mixed management solution. For us, it was very interesting as a tool to support research. It would give us the possibility to cooperate with other research groups through the local and the national research network without entering in conflict with the university IT services. And one objective we really wanted to have real users connected to real services, because we felt that doing experiments with OpenFlow switch, trying a telnet to a machine, establishing a server, trying your browser on a virtualized network, it's interesting, but I think you don't find real limits of the solution. So that was the starting point of our network. In our network, this is the part that was at that time run by the university IT services, and we had the opportunity to get a link to the National Research and Education Network experimental facility through a link that was given or lent to us by our local, the Basque Country National Research and Education Network, which is I2Basque. So that meant that first we have to discuss with the IT services that there was a connection to our laboratory of a network from another side, because even if we are all Basque, there are differences. This was somewhat difficult to understand, but anyway, those guys weren't able to give us the service we needed, so they agreed to have this solution. But it was not very clean, because in fact, we had the written definition of the cities. We were not able to switch ports. We had to be very careful managing the equipment. It gave also the problem that it was not possible to do some research in practice labs or in other parts. At that time, the services were defined by VLANs, because the university service defined VLANs. That's very normal, which in fact for us was a problem, because in some other networks you also use the VLAN for doing experiments. So you have to think somewhat. There are always solutions, but it's not so streamlined. So that's the solution we have developed, and we are now trying. The idea is to have most of the equipment is NEC switches. We have a 10 gig backbone up to the point of presence of the National Research and Education Network, and we support mixed traffic on every of these links. In the I2Basque link, we only support experimentation, because per political or technical requirements is the way to be done. And this is the idea. We use for this in-band signaling. I mean, we rely on the own network for transferring the signaling. And as we will see, the modules have been developed over NOx. Well, we had already a triple-E solution available, and our objective was using it for accessing some experimental slices and also a production slice. The net result of this would be the possibility to configure a set of flows, which in fact are a set of OpenFlow rules, to define a service as a result of a successful triple-E process. There were 3 issues to be solved. One is the interaction of OpenFlow with the legacy protocol, for example, the .1x. Another one was how to deal with the OpenFlow-based configuration. And the third one is how we define a framework to be able to slice the infrastructure for every slice. Well, the interaction with .1x was more or less straightforward. Every time a PC starts a process, a dialog, the OpenFlow switch detects that frame, because it has the third type, this third type, and this multicast address, and it has a rule defined that sends that frame to the NOX. The NOX implements not the NOX itself, but the process running in the same machine at the NOX, implement a modified host IP. We are able to take a decision at an authentication authorization server, and as a result of that, we can control the access to the network of that switch. The second part is how we configure the OpenFlow switch. We have developed a module based on REST, which receives a profile which is generated upon a successful authorization using a service definition database. This is sent to the NOX module on the controller, and this controller configures not only what switch, but the switches that are needed to define data slice. The control framework for traffic isolation. Well, by now we support 3 slices. One is the production slice, is what we define. The access to internet is the standard service offered by the university. You can access the services. And we have actually 2 different slices. One that is running our work in OpenFlow on access networks with CMTS and GPON, and another which runs the prefix-based forwarding the decision experiment. For this, we had to have some extra functionality to be given to FlowVisor. One is the support for MAC address prefix-based delegation. We use the network slicing that follows the Geyser model that you have seen elsewhere, and we also had the corresponding FlowVisor. So in some way, this is the physical infrastructure. This is another thing we are developing, but it's not real time, which is a neutral access network for experimenting. We have the production slice, and we have an slice traffic. How we did implement the slicing? We implement the slicing using MAC addresses. For the production traffic, we use globally administered MAC addresses. Those are MAC addresses that have, I never remember, but I think it's the second bit put to 1. So FlowVisor, every time there is a rule that affects this kind of traffic, everyone it receives one of these MAC address has to search for that bit. That's the way we difference the production traffic. This is interesting because we don't need to change anything on stock machines that are connected to the internet. There is standard MAC addresses using standard services. We only need to make a difference when we are directing at the OpenFlow level. Well, the research traffic uses locally administered MAC address. These are addresses that have the corresponding bit set. This means that we must give to every machine a MAC address. This is not a problem, because anyway we are doing network research. There are 2 possibilities. One is the statistical assignment, and another one is using a protocol we have developed. It was published some time ago, like LACP, but it was confusing, so we changed the name. This is running with Ubuntu, and it works fine. How many experimental slices we can have? We will define the slices, as we will see, as the first 14 bits of the MAC address. That means the first 16 except 2. One special issue that is common to every OpenFlow development is that you need to identify the multicast and broadcast traffic, because this is the kind of traffic you don't want to propagate through the network. So this means that, for example, for ARP, you need to develop, we have developed a module that is DHCP based, so it's able to snoop the DHCP using the DHCP traffic, or is using to use the IP traffic from known MAC addresses. Just a quick update on the experiment. The prefix-based forwarding decision experiment is just a proof of concept experiment that is able to be run in this kind of technology. And that is interesting because you should not be able You are not able to run this kind of experiments in a normal Ethernet network. What we do is we aggregate the foregrounding rulers by the aggregation of using a common, well, we aggregate the rules using a prefix on the MAC address. Just before anything begins to speak, it's not Portland addressing a scheme. Portland has another uses. It's more used for scalability. With PFD, we can also support virtualization. In Portland, you need a MAC rewrite. Everything you make the last hop. And in our setup, you use the sign address. This is the slice identifier. This is the 8-bit switch identifier. This makes 24 bits. This is an implementation issue. We could have with pure 1.1 and following version OpenFlow, we could have this of anywhere. And it's interesting because this gives you information about the position of every switch. This means that, for example, you can have some capabilities. You are able to make now traffic engineering on the layer 2. The location of the systems is known. Just once you get a new system, you can configure the rules automatically. You don't need any learning. You don't need treats. You can even use different paths for going from one system to the other. And there is a great reduction in the number of forwarding rules, as you see. The rules are isolated from customer. This is, we plan to have the authentication part of this solution available, but it's still dependent on too many old modules as Knox, as Flowvisor. Lessons learned, well, that is very important to get the IT services and your national research network aware of it. This is a public thank you to both Rediris and I2Basque. It's also a thank to our IT services because accessing to do some experiments is not so easy. It's also interesting to see how real IT work, because it's interesting for students, for PhD students. It's not so easy to put a system on a rack. You have some paperwork, but I think it's interesting because it settles a relation that is later used. From the technical side, well, using software-defined network is cool. I think it's interesting, but you must need many things, and you must write by yourself many codes, at least until the OpenFlow ecosystem is fully set up. We also found that Flowvisor is not so transparent as it is supposed to be. It's also very important to have a highly motivated team. We have the chance to have that team. And it's really interesting because I think it really opens the possibility to doing experiments. The future work, we really would like to increment the number of users and see what happens. We are now in the best moments using 50 to 70 users in the first both users and servers and 3 slices. We are seeking to participate in other OpenFlow experiments. Ophelia is underway, and I saw this morning that there was effort in Jan and OpenFlow, so we're really happy in participating in this. And in upstream, we would like to OpenFlowize our local national records and education network. We would like so to continue to converge on accepted virtualization models and contribute. And for the product, we are waiting for some stabilization. So this is the last slide. I publicly acknowledge the work of my colleagues, John, Victor, Alaicha, and Borja. Thank you. If you have any questions, you're welcome.
Okay. Thank you. Yes, 5 minutes for floor is open. It's clear.
It seems.
Or vice versa.
First of all, thanks for the presentation. It's cool to see real work. It's always good when people talk about the real work that's happening. There are a number of other open source controllers now starting to pop up. What's your current view on Nox versus Pox, which is a Python version, versus Floodlight versus Trema?
No.
Any view on particular what the research is going to happen there?
Well, we have been in the process of selecting the next OpenFlow controller, and our view is that perhaps the more interesting option by now is perhaps Floodlight, because of the idea they have of supporting both an open source and both a commercial version. I mean, this is in this world, you really don't know if you are aligned with the work they are doing at the OpenFlow networking. If you follow the traces of someone that is deeply involved, I think you can have, as a research group in the university, to contribute perhaps in a more commercial oriented, in a more straight way. So perhaps this is still a hot issue in our research group, but we think that mostly sure it will be for Floodlight. Thank you.
No more questions? No, there is no question. So thank you again.
Thank you.
And third talk, which would be again about the OpenFlow somehow. It's a talk of Eric Puyul from LBL. Originally, it's one of the co-authors in the manga, and yeah, Brian. Okay, Carpenter. No Carpenter.
Okay, good afternoon. My name is Eric Puyol, and I'm working for the Energy Science Network, which is part of the Lawrence Berkeley National Lab. Today, I'm going to talk about how OpenFlow can help intensive data science. So first, let me tell you quickly what is ENSNet, because perhaps you haven't heard about us. We are funded by the Department of Energy, the Office of Science, and our goal is to provide a scientific network for all the DOE facilities, scientific facilities. For that respect, we currently have a 100 gig network, which is basically, the footprint is about the entire nation. We have built that with Internet 2. We have optimized and designed this network to provide facilities to do very large flows. Scientific networking usually requires very large flows. We currently have about 40 DOE sites that we are connecting, and we are pairing with about 140 commercial or other scientific networks. Some people could ask, why actually do we need to have a specific network for science? After all, there's a lot of networks around the world. Well, the reason is, when you want to do science, and especially large data science, you need to have some particular services that typically commercial entities do not provide. One of them specifically is to be able to provide on-demand circuits that will have a guarantee of bandwidth. We also provide some testbed because, of course, when you want to be on the edge, you kind of have to experiment with new protocols, new technologies. And another aspect of us are people. We have actually a world-class set of network engineers that are working directly with our users to make sure that they achieve their goals. So I was tempted for a while to put like a graph with the growth of internet traffic and so forth, but we see those kind of graphs every day. It goes up pretty quickly. But now let's try to see why actually we have such an increase of bandwidth. So on this slide, you can see actually the visualization of exactly the same data set. The data set is actually the evolution of the universe from the beginning until now. And this is that was an animation, and those were actually two identical frames. On the left side, you can see that display over a 10 gig pipe. On the other side, you can see exactly the same data set with a 100 gig pipe, 10 times more. And as you can see very well, it kind of looks like on a 10 gig path, you have a very sparse universe, almost empty. And on a gig path, you don't even see the stars. It's just like almost like full of everything. If you were a scientist and you were doing experimentation, I'm pretty sure you prefer to see the 100 gig data set rather than the 10 gig data set. So this is really why we need to make sure that we can provide higher performance pipe, so researchers can do better research. So sciences, there's a lot of sciences around the world. Physics, biology, climate, they all are different. They all do different kind of experiments with different goals, but they do bear some common traits. And as you know, from the point of view of networking, that's even more true. Typically, what you would have is a flow, a workflow when actually you have an experimentation with perhaps an instrument that will generate petabytes of data. At some point, you will have to move this data set into a different location where you will be able to do the processing. Because typically, you don't have a supercomputer next to each instrument. They are too expensive. So you have to move data to the supercomputer so you can process your data. And perhaps even you will have to do some visualization later on. We have different kind of flows, but some are more real-time than others. But typically, that's you have a read, you transfer, you write, and you process. If we don't do that right, if we are not capable of bringing the amount of data that the scientist needs to the computer, we'll have some consequences. One of them is you will not be able to run your instrument at the same resolution that you would like to. You have to go with the empty universe. And if you go with the empty universe, at the end of the day, you will produce less science. So if you want to abstract this a little, what does it mean to bring high-performance data to the computer? Well, first of all, we have to see what is the problem. Typically, the instrument is not going to be connected directly to the WAN. No, the instrument is going to be somewhere. It's going to be connected into the LAN on your site, and eventually that will go into the WAN. Which means that if you want to provide the same quality of services, if you want to provide actually quality of services from the source to the destination, you need to make sure that you have the same quality of service between the LAN of the source, the WAN, and the LAN of the destination. That almost never happens. You have some problems. Perhaps you will have the same bandwidth reservation. Perhaps things will not be configured correctly. Another important aspect of being able to move data is automation. Typically nowadays, if you want to transfer, if you want to have like, I don't know, a 10 gig path between one part of the world to the other side of the world, you will have to contact a lot of different network engineers on the path to make sure that you have your circuits. It is possible, and actually that has been done, but if you want to repeat that operation 10 times a day, you cannot call the same engineer 10 times a day, because the second time, basically, you will get no answer. So you need automation. You need to have guaranteed bandwidth, because you cannot have high performance without guaranteed bandwidth, of course. And the last point, which is actually very important, is we will need to have an end-to-end pipe. Being able to transfer data from a source to destination is not just the problem of the WAN, it's an entire system. You need to be able to have a pipe when actually the end host can decide what kind of protocol they want, because not all protocols are good for just any kind of science. Specifically, and for the purpose of this talk, we have been investigating non-TCP/IP protocols and remote DMA. For this, we're using a protocol which is called ROCI, that stands for Remote DMA over Converged Ethernet. And that's a layer 2 protocol, meaning non-IP. So fortunately, we are in 2012, and the world hasn't started now, and we have already some solutions. Science has been happening before. One very important tool that we've been using is the inter-domain protocol, control protocol. That protocol has been used by different network providers, ESNet, Internet2, Giant, and some others. And basically, each domain will run an IDC, which is a service, which, of course, implement this protocol. And between all those services, they will negotiate to be able to create a virtual path from one end to another. So that actually works really well, and has been deployed and used for many years, and many scientists rely on those services. It has a reservation system, which is really cool. So for instance, you could say, tomorrow between 10 a.m. to 11 a.m., I need to have a 20 gig path between this site to this site. And you will have it. There's nothing else you need to do. You reserve, you get it, and you can use it. It's being deployed, as I said, and we have different implementation of this protocol. ESNet and Internet2 has developed a particular software called OSCARs, which actually implement this protocol. One of the issues of OSCARs, which is not an issue, but that's kind of the way it is, typically one circuit ends at the border of the site. You do not want OSCARs, you don't want the one to control your switch or your router. So that means that's not truly end-to-end. Another exciting technology that we definitely heard today is OpenFlow. OpenFlow, in a way, is very similar to OSCARs, because it's going to dynamically carve out a path, perhaps even a layer 2 path, between a source and a destination. So I'm not going to go into detail on how OpenFlow works, because fortunately we had an excellent presentation a bit earlier. But the way I'm going to use OpenFlow for this particular goal, I'm going to use two particular characteristics. One, of course, is the ability of detecting new flows and being able to program the switches to set a particular path for a flow. So basically, you have a new flow. The OpenFlow switch will say, oh, that's a new flow. We ask its controller, what should I do about it? And the controller, checking some whatever it needs to check, will say, well, either forward or drop. And that's how layer 2 packet can move from a host to a destination. Another feature of OpenFlow that is being used here is the ability of doing dynamic topology discovery. OpenFlow is capable of discovering other OpenFlow switches in their network. This is network. That's using a Hello protocol, LLDP. Each switch sends on all its ports, an LLDP packet saying, oh, here I am. Other switches will get the packet and say, oh, cool, here you are. The way we have been a little bit using this is actually to even incorporate the end host, the computer, part of its discovery, as I'm going to explain a bit later. Okay. So usually when we see OpenFlow or topology, networking topology diagram layers, we start from the network element and we move up into the application. I wanted for once to go the other way, going top-down. Because actually, when you think about it, when you want to transfer a file, that's always the application that decides to transfer a file. That's not the network that says, oh, by the way, if you have a file to transfer, here you are. So we start by the application. The application only knows I need to transfer a file from host A to host B, and that's all it knows. It doesn't know anything else. It doesn't want to know anything else. You don't want the application to know anything about the real topology whatsoever. In a way, think about doing an SCP. Even though you probably don't like this command, but when you do an SCP, you just give source and destination, and that's it. So that's the topology that an application sees. Here, I'm adding a new layer, in a way, a session layer, which basically, that's the middleware. And there's different middleware that you can see. For instance, think of this as cloud control management, or Globus Online, or different software that actually manages a state between the source and the destination. So this layer actually has a better view of the topology. Of course, it knows host A and host B, but it will also know that host A is into site A and host B is into site B. It will also know something very important, that it is capable of connecting the two sites together. However, it doesn't know how. And that's where the network controller comes in. The network control understands better the topology. It will, for instance, understand that the domain, the one, is controlled by something called OSCARs. It will know about this service. It will know that it can request a circuit. It will also know what kind of technology, if any, is on each of the sites. So, the topology is a bit more complete, but still doesn't know how to provision. And for this, it uses actually some technology-driven controllers. So they're actually also network controllers, one for the LAN and one for the WAN. So the LAN, of course, will be OpenFlow. And as you can see, it will understand all the switches of the site. But we also know actually what is the OSCAR circuit that's being used, and perhaps even know a little bit more of the topology. So now I'm going to concentrate mostly on the network control layer. We call it Excel, and please don't ask me why. And basically, this is network control, which is going to act almost like an IDC. And I will explain why. When you think about it, OSCARs already does most of the work. You tell OSCARs, I want some circuit from point A or point B, except those are not the right endpoints. So one could think, well, let's extend OSCARs to control the network at the site. How many of you would like OSCARs to control your network? Not that many, right? So here we have a simple problem of administrative boundaries. OSCARs cannot and doesn't want to control your network. So we have a problem, we need something else. Also, OSCARs is one technology. As you all know, when you have a wide network, you always have new paths, new routers, new links, or perhaps failures, or things like this. But in a way, it's rather static. I mean, it doesn't change every second, at least not for our network. When you go into the LAN, you're going to see much more dynamic evolution. In a way, think about the way you work in your place, and you have a laptop. You are connecting your laptop into your desktop, and then you go into meeting room, and you're going to connect there. You just change the topology. So topology is much more dynamic, and OSCAR probably is not capable of doing path computation on such a dynamic network. The last current restriction we have with OSCARs, it's actually strictly point-to-point. Unfortunately, applications, and again, think about cloud computing, would probably have multi-point to multi-point on their own side. That doesn't mean that they won't have a single point-to-point link between the sites, but they will fan out. However, OSCAR is a good software, and it's a production level, so we're not using it. So the idea was to modify OSCARs to make it work for what we want. Just like OSCARs, Excel will have to be deployed on each of the sites, because basically we are seeing now 3 different kind of domains: site A, the one, and site B. Let's go a little bit more into details. And so this is the block diagram of Excel. As usual, I will start by the top. And you can see that actually you have what is called the Excel IDC API. This is strictly the IDC API. In other words, if your application is already capable of using OSCARs, it will immediately be capable of using Excel. Same API, same semantics. There's 2 sorts of users of this API: the session layer, of course, but of course also the peer site. Basically, if you're on site A will use this API to communicate with site B. The bottom API, you can see you have 3 different boxes. The end host is basically where the end host is going to register and say, this is where I am in the OpenFlow topology. I say it's a layer 2 because basically that's the goal. Same way, you can register OSCAR circuit by using OSCAR's registration API. And since OpenFlow switches can discover themselves, they can register their own topologies to the OpenFlow controller, which is embedded in Excel. At the center of Excel, you can see this box that says local policy-based path computation. That's what it is. Basically, every time you want to compose a path from each ends, you need to be able to make that path. So you need to compute it. However, you need to compute it accordingly to some rules. Rules are going to be, obviously, some sort of authentication and authorization. You have notion of users. But also, what kind of resources this particular user or this particular project can use. And so that's what all this PC is going to do is, basically, this is your path. A little bit more detail on the auto-discovery. As I said, basically, the switch, an OpenFlow switch, will send an LDP packet, hello packet, to all of its ports. If you have a host connected to it, it will receive such a packet. Typically, hosts don't handle LDP packets because this is not for them. So what we did was to implement a little daemon that we run on the host that listens to those packets. And in those packets, they will get very valuable information. They will get, oh, I am connected to the switch with this particular ID on this particular port. So basically, it knows where it is. When it gets this packet, it will register itself to Excel. The one registration is a little bit different because, first of all, it's not easy to capture a LDP packet on an OSCAR circuit, but also the nature of how you create those circuits is a little bit different. There's basically 2 different kind of scenarios how you create OSCAR circuits. The first one, you will have network engineers who are actually going to create a circuit for you. those circuits, in a way, are manually created, and they can be inserted manually, registered into Excel. Another way for an OSCAR circuit to be created for Excel would be by Excel itself. The policy can be implemented in such a way as if there is no one circuit available, we can just create one dynamically. And in that case, Excel will ask those OSCARs to create a new circuit. The same way, of course, OSCARs will have to teach Excel where it is connected to the LAN OpenFlow network. So the way the path computation works is basically based on, I said, on of N of Z. And you can attach particular metadata to each of the resources, either the OpenFlow switches or even the OSCAR circuits. Those metadata can contain things such as this circuit has been provisioned for this particular project. One circuits are expensive, they cost. So you may not want necessarily to share one circuit with just everybody on your site. So you have the ability of basically tagging resources with particular users or projects. So that is actually how Excel can manage to find out what is the right resource for you. Another very important aspect of how it's being done is to deal with the dynamic aspect of a LAN. OSCARs being a reservation system, an advanced reservation system, that means if you have any change of your topology, your path is dead, you have to recompute it. You cannot do that in a LAN. So instead of computing the path at the time of the reservation, you will compute the path at the time of the instantiation of the setup of the path. And that's basically a dynamic path computation. Using quality of services of OpenFlow, you can actually then decide you can have some bandwidth reservation. Unfortunately, by the OpenFlow version we used at the time didn't have QoS, so we were not able to implement bandwidth reservation. But that would be possible with the future version of OpenFlow. So let's go now into the workflow, how a reservation is made. So just like the previous slides, when I had all the topology, everything starts at the application level. The application decides, I want to move files from A to B. So what it will do, it will simply tell the session, I want to do that. The session gets this particular request, and it will decide, oh, this is a big file. Let's use remote DMA, it's much better. So I need to have some resources that can deal with remote DMA. So it will know that it will have to request network layer, Excel, to get some particular path. Excel in turn will actually, using the IDC protocol directly, will talk with the remote Excel on the remote site and will negotiate the path that it has just computed. Just like the same way OSCARs works right now between domains. When that's done, the reservation is made, and basically you just need to wait until the reservation starts. When the reservation starts, OSCARs will actually provision itself. I mean, that's the great thing about OSCARs. You don't have to worry about it. It just happens. So the only thing you need to do at this point, what Excel needs to do, is just to wait for the notification for the OSCAR circuits to be up. At that moment, it will actually look at where the end host is connected on each of the sites, configure all the switches for the proper path. Since that's remote DMA we are talking here about doing a selection based on the ether type, because that's not the same as IP. So that's what you want. That's how you can actually forward layer 2 circuits, layer 2 packets. It may also have to do some sort of VLAN translation at the border, because changing the VLAN on a pre-established OSCAR circuit is not really easy to do. So that's perhaps some VLAN translation that needs to be done. When that's done, when the path is basically provisioned, Excel will notify the session layer using actually exactly the same mechanism it was notified from OSCARs that the one was provisioned. And in turn, the session layer will notify or start the application for the transfer. We actually have implemented it. And in fact, we even have demonstrated it. Last November at Supercomputing and Seattle. Seattle is on the west coast of the US, on the Pacific coast. We had two different endpoints. One which was located in Seattle on the booth, and that's what you can see on the bottom circle, LBNL ESNet booth. And the other end was actually in New York, in Long Island. That's what you can see on the other side. The entire demo was a collaboration between Indiana University and University of Delaware, and also NEC. And what we provided was an entire stack from the application down to Excel. The application was actually some version of Grid FTP, which was modified to run our remote DMA. And we are using Globus Online as the session manager. So basically, the flow, you can see that you have Excel that runs on both of the endpoints, and Excel controls the OpenFlow network on each of the sides. So basically, the only thing I need to say there is actually, if you don't know the geography, the distance between the two sites is about a few thousand miles. It worked. And when you do a demo at supercomputing, actually, that's pretty cool when it works. Not only it worked, but actually even got the result we wanted to see. So you can see in the chart different comparison between the various protocols and the tools. The path was the same, exactly the same in all the cases. That was a 10 gig clean path. So using a new TCP, which is benchmarking tools, you can see that TCP was doing at 9.9 gigabit per second on the 10 gig. That's pretty good. All tuned up, of course, you know. And UDP was also doing 9.9, so about the same. Expert test was actually a custom test we wrote to be able to do comparison between TCP and RDMA. And you can see that, you know, TCP was doing 9.9 and remote DMA was doing 9.7. So it's a little bit less, but quite close. And if you think that Rocky was initially developed to run on an InfiniBand network on the back plane, meaning with basically no latency, and a really reliable network, that's actually pretty cool to be able to run the same protocol over a very long distance with no modification, and it actually works. But now the most important thing is actually on the other chart. And you can see basically the CPU utilization per protocol. It's hard to see the remote DMA because actually it's barely measurable. But you can see memory to memory, which is really what matters the most. If you use TCP, you would use about 60% of your CPU just to send data. If you use remote DMA, actually that was 3%. It's hard to see here. It was 3% versus 60%. If you use disk, of course, I mean, if you do disk to disk or disk to memory, of course, you have the cost of doing the disk operation. But you can still see that remote DMA is still much better. That is very important because if you can imagine that at 10 gigabit per second, you use 60% of your CPU to run TCP, what is it going to be when you run 100 gig? So, impact and future. So first of all, we have demonstrated one more time how powerful OpenFlow is to be able to bridge the endpoints to where it needs to go, whatever the protocol you want to use. That is actually yet another demonstration of how good is OpenFlow. And it was actually really easy to do. So OpenFlow was really a natural mix with OSCARs. We also see that being able to do that allows us to be able to do layer 2 protocol, perhaps even from your laptop eventually. That would be pretty nice to be able to do remote DMA from a small device to a storage because, again, it's about CPU. However, we see that in order to do this, we need to provide something like Excel, which means the end site needs to provide their own local provisioning. Remote DMA, in my opinion, is very important because, first of all, it did work, so that was pretty nice. But also, you have to realize that a lot of NIC manufacturers start now implementing in standard remote DMA in their NIC. So remote DMA, in my opinion, is not going to disappear. It's going quite the opposite to be around. I don't know for sure if that's the right technology, to be honest with you. But what I'm convinced is we will need layer 2 protocol if we want to achieve higher throughput. But as I said, if we want to do this, a site will have to deploy particular services. And of course, application will have to implement remote DMA. We had actually have to modify some remote DMA. So my last take, this is my last slide. If we don't do anything, having higher performance network will not help until we can basically be able to do layer 2 protocol. Questions?
Hi, there was recently quite a bit of press about Google moving to using OpenFlow across its data centers around the world. Do you know whether they're using OpenFlow entirely or whether they've got some system like you described to work between the data centers?
Not as today. I don't know about it. I had once a discussion with some Google engineers about this, but I don't know. Basically, I don't know. I would not be surprised if they use something similar.
Question on the
sure.
all the multi-domain aspects are dealt by the Excel. You're not making multi-domain OpenFlow or making anything in that direction, right?
So I couldn't.
I mean, you're connecting different domains,
right?
And when connecting different domains, you are relaying for all the multi-domain operation in the Excel middleware. You're not addressing anything in the direction of multi-domain OpenFlow or controller-to-controller communication, or,
well,
or are you?
Basically, if you think again, if you just look at those cars, it is already a multi-domain protocol. So, but the IDC protocol is actually what bridges domains together, and that's basically by suggesting a path. You ask the other side, do you agree with my path? And if you say yes, then let's do it. So Excel does the same thing. And if you abstract the notion of domain, considering a site as a domain, because it is a domain, but not necessarily as an OpenFlow domain, but as an administrative domain, then you can start using the same sort of authorization and authentication to do exactly the same thing. Is I have a resource, a local resource that I'm ready to share with you for this particular path. Is it okay with you? So in a way, it is multi-domain. Now, I am absolutely not saying that a same controller will control different domains at the same time. That I'm absolutely not advocating for. I'm advocating against. But in the end of the day, it's still an end-to-end multi-domain path. Exactly. Absolutely.
So do you maintain topology and available bandwidth database for local area network in Excel?
Could you please repeat?
So do you maintain topology and available bandwidth information of local area network?
Right now, no, we don't. And we don't for two different reasons. Because number one, what I would really like to do is to use the QoS capabilities of OpenFlow, which were not yet available. So that's what I really wanted to do. But another way I was thinking about doing it is instead of maintaining a database of bandwidth which is available, which actually you don't really know on the LAN what's going to happen, is instead of doing that, is to run benchmarking, measurement of what is the current capability. And see if you consider that perhaps if all your OpenFlow network is controlled by the same controller, you could actually know ahead of time how much bandwidth you will have left. So you don't really need to carry database, but just look at what you've got at this particular moment, get the path, and then make sure that nobody else can take off anything from your bandwidth.
But even if OpenFlow supports QoS, what if requested bandwidth is not available at the time of provisioning?
That would be an issue, I agree. I would say, the real answer here, Excel is a demo gear. It's not a production level. Oscar is production. So in a way, Excel works pretty well because it's using production level code. But when you implement your policy, I mean, your local policy, there's many things you may want to do, and not necessarily only bandwidth reservation. That's just one of it. And if you want to implement something which have a database just like Oscar does, you can do it. That would be absolutely no issue. But the point here is the policy on site A does not need to be the same as the policy on site B. One can do something in a particular way, and the other one can do something else in a different way. You actually do want this separation. So that's why I didn't put too much emphasis on how the policy was going to be done, because in a way that was almost irrelevant. Any other question? No? Well, thank you.